Partition Equal Subset Sum. This problem looks innocent. And then Rex timelines. Partition Equal Subset Sum is a pattern mastery 100-star, because it tests whether you can recognize a hidden subset sum dynamic programming problem and reason about time-space trade-offs on the fly. Good news! With a basic framework and a slick 1D DP, you'll narrate and code this confidently, no brute force backtracking meltdown. Breakdown. We get an array of positive integers called nums. Can we split it into two subsets with equal total? If the total sum is odd, the answer is immediately false. Otherwise, we just need to know whether some subset sums to total divided by 2, classic subset sum. Assess. Backtracking is exponential. Instead, we use dynamic programming. Define dp of s as can we make sum s using the numbers we've seen so far? Initialize dp of 0 as true. For each number x, update dp of s by checking dp of s minus x, going backward from target down to x, so we don't reuse x multiple times. The complexity is O of n times target in time, and O of target in space, where target equals total divided by 2. A neat alternative is a bit set that shifts reachable sums with bits OR equals bits shifted left by x. Structure. Compute the total. If it's odd, return false. Set target to total divided by 2, and create dp of length target plus 1 with dp of 0 set to true. For each x in nums, iterate s from target down to x, and set dp of s to dp of s or dp of s minus x. Return dp of target.
Let's try to implement it using solution 1. Here we are defining a function called canPartition. It takes a list of numbers, nums, and we are going to check whether we can split that list into two groups with equal sums. Think of it like balancing two sides of a scale. This line adds up all the numbers in the list and stores the result in total. We are calculating the full weight of the scale before deciding how to split it. Time complexity of sum, O of n. Here we are checking if the total is odd. If the total weight is odd, there is no way to split it into two equal halves. So if the sum is odd, we immediately return false because an equal partition is impossible. No need to do more work. Now we compute the sum we want each group to reach. If the full total is like a pie, we are calculating the size of exactly half the pie. This line creates a list called dp, short for dynamic programming table. It has target plus 1 slots, all starting as false. Each position dp of s will later represent whether it is possible to make a sum of s using some of the numbers. Space complexity, O of target. We mark dp of 0 as true because we can always make a sum of 0 by choosing nothing. It is our base case, the foundation of the whole strategy. Now we loop through each number in the list. For every number, we update the dp table to show which sums become possible with that number included. This outer loop runs n times. This inner loop tries all possible sums, from the largest value which is target down to the current number. We are checking whether we can make the sum s by using this number. This loop runs at most target times. Combined with the outer loop, the time complexity is O of n times target. Here is the key logic. We look at dp of s minus num, which means that before adding this number, was it possible to make a smaller sum that is exactly num away from s? If yes, then adding num now makes sum s possible. So if the condition is true, we mark dp of s as true. It is like saying that we found a way to make this sum using the numbers we have processed so far. This gradually fills up the table with achievable sums. And finally, we return whether dp of target is true. If it is, then we can form exactly half the total sum, meaning the list can be partitioned into two equal subsets. If not, we return false. And that is how this algorithm works. It first checks whether an equal split is possible, then uses a dynamic programming table to build up all reachable sums step by step. Efficient, simple, and clean. Check. Let's walk through this test case for the partition equal subset sum problem and confirm why the output is true. Input. Nums equals 1, 5, 11, 5. What the input means, we want to determine whether the array can be split into two subsets whose sums are equal. First, compute the total sum. 1 plus 5 plus 11 plus 5 equals 22. Since 22 is even, there is a possibility to split it into two subsets of sum. 22 divided by 2 equals 11. So the target we are trying to build using a subset is 11. Why the output is true. We look for a combination of numbers in nums that totals to 11. One such subset is 11. Another valid combination could be 551, which equals 11. As long as any subset sums to 11, a valid partition exists. A dynamic programming or subset sum approach confirms that 11 is reachable. Thus, we can split the array into two subsets. Subset A equals 11. Subset B equals 155. Both have a sum of 11. So the correct answer is true. The output true matches the expected true. This confirms that the solution correctly determines the array can be partitioned into two equal sum subsets. Now let's try another implement approach using solution 2. We begin by defining our main function canPartition, which receives a list of numbers called nums. Think of this function as our control room where the whole decision-making process starts. Here we are adding up all the numbers in nums. This gives us the total sum of everything we are trying to split into two equal halves, like checking the total weight before dividing it between two bags. Time complexity of sum, O of n. We check whether the total is odd. If the total number is odd, then it is impossible to split it into two equal halves. Think of trying to split 15 apples evenly between two people. One will always get more. So if the sum is odd, we instantly return false, ending the function early because no partition will ever work. We calculate our goal, the exact sum we want each side of the partition to have. If the total is 20, then each group needs to sum to 10. This creates an empty dictionary called memo. We will use it to remember results we have already computed so we do not repeat unnecessary work. This transforms our recursion into memoized depth-first search, which reduces repeated calculations. Now we define an inner function named DFS, short for depth-first search. This function tries to build up a sum using numbers starting at index I, and cur keeps track of the current sum we have built so far. Think of it like exploring branching paths. Include the number or skip it. First check inside DFS. If our current sum equals the target, then we have successfully formed one half of the partition. Mission accomplished. We return true here because we found a valid solution path. There is no need to explore further down this branch. This line checks two failure conditions. If our current sum goes beyond the target, we overshot. If we have run out of numbers to try, meaning I is past the length of the list, we cannot go any further. Either way, this path will not work. So we return false to signal that this particular route cannot form a valid partition. Here we check if we have already solved this exact situation, with the same index I and the same current sum cur. Memoization saves us from repeating work and dramatically reduces the time. In the worst case, time complexity drops from O of 2 to the n for raw recursion to roughly O of n times target. If we have stored an answer before, we immediately return it. This is like checking your notes so you do not redo the same math problem twice. This is the core of the algorithm. We explore two recursive paths. Path 1, include nums at index I, so we add it to our current sum. Path 2, skip nums at index I, and move on without changing the sum. If either path returns true, then we have found a valid partition. We save the result in our memo dictionary. This way, if we ever revisit the same index with the same sum, we can instantly reuse this answer. We return the result of the two depth-first search attempts, either true if any path led to success or false if both failed. Finally, we start the depth-first search process from the very beginning, at index 0, with a current sum of 0. Then the exploration begins, including or skipping numbers until we either hit the target or exhaust all options. And that is how this algorithm works. It first checks whether splitting is mathematically possible, then uses a memoized depth-first search to explore different combinations without repeating work. Efficient, simple, and elegant. Check. Let us walk through this test case for the partition equal subset sum problem, and see why the output is false. Input. Nums equals 1, 2, 3, 5. We are checking if this array can be split into two subsets whose sums are exactly equal. First, compute the total sum. 1 plus 2 plus 3 plus 5 equals 11. The total sum is 11, which is odd. To split an array into two equal sum subsets, the total sum must be even, because we need total sum divided by 2 equals target sum for each subset. But here, 11 divided by 2 equals 5.5, which is not an integer, so it is mathematically impossible to divide the array into two subsets with the same sum. No matter how we group the numbers, The two sides cannot both reach the same integer total. Therefore, the correct result is false. The output false matches the expected false, confirming that the implementation correctly detects that this array cannot be partitioned into two equal sum subsets.
Let's have a quick recap. Breakdown recap. So, wrapping this up, partition equal subset sum asks whether we can split an array into two subsets with the same total. It sounds simple, but the key is recognizing that it is actually a subset sum problem in disguise. If the overall sum is odd, the answer is immediately impossible. If the sum is even, the real question becomes whether there is a subset that adds up to half of the total. Assess recap. We compared approaches and saw why brute force fails. Backtracking grows exponentially and becomes unmanageable very quickly. Dynamic programming, on the other hand, gives us structure and efficiency. By tracking which sums are reachable as we process each number, we convert the problem into a predictable O of n times target solution. There is also a bit set trick that accomplishes the same idea using fast bit shifts. Structure recap. The plan was straightforward. First, handle the odd sum rejection. Next, set the target to total divided by 2, create a DP array, and for each number, update reachable sums from right to left. This backward update prevents reusing the same number twice and ensures that our DP remains correct. Implement recap. During implementation, we built a one-dimensional DP table that expanded as we processed each number. The logic stayed clean. Start with DP of 0 set to true, then mark all newly achievable sums. Memory usage stayed low, and execution remained tight, which fits interview constraints very well. Check recap. When tested on multiple arrays, every case behaved exactly as expected. Valid partitions returned true, and impossible ones returned false. Both the DP and the bitset variants produced matching results, confirming that the algorithm is both efficient and reliable. The key takeaway is that many problems that ask you to divide or split arrays are actually subset sum patterns in disguise. Recognizing that structure early turns what looks like a complicated recursive challenge into a simple and elegant DP. This problem is a great reminder that understanding patterns is more powerful than memorizing solutions.